In this series of figures, we want to look at oxygen exchange across the respiratory membrane, both at rest and during exercise. At the top here on the left, we have the resting conditions. And we see that our alveolar PO2 is 105 millimeters of mercury. This is maintained through resting ventilation. Below that, we have our capillary blood flow. This has lower oxygen, and therefore oxygen will diffuse in the net direction from alveolar air into that pulmonary capillary blood. We can see that graphed here at the bottom as we pass through those pulmonary capillaries. We come in to those pulmonary capillaries at a partial pressure of oxygen of about 40. This is blood that just left the systemic tissues where it became partially deoxygenated. It now returns to the heart and then goes off into the pulmonary circuit to become reoxygenated. We pass that blood across this high PO2 of about 105, and what we see is that we rapidly equilibrate between the capillary blood and that alveolar PO2. We actually equilibrate within 0.25 or a quarter of a second, despite the fact that it takes nearly 3/4 of a second to pass through that pulmonary capillary. This means that we reach equilibrium well before we get to the end of the capillary. This seems like a bit of a reserve that we're not using. We're not gaining any more oxygen in the latter half of this pulmonary capillary. Well, let's come over to the right here during exercise. We still maintain our alveolar PO2 of 105 through increased ventilation stimulated during exercise. However, our pulmonary capillary blood flow has now also increased dramatically. Cardiac output has gone up several fold. This means that we're going to spend less time in those pulmonary capillaries with the blood flowing more quickly, only about 0.25 seconds. Also, our gradient has gotten a bit bigger, driving oxygen into the bloodstream. The pulmonary arteriolar blood is now at about 20. This is because this was systemic venous blood that's passing through our muscles and giving up more oxygen than normal, and therefore the PO2 falls from about 40 at rest down to about 20. This gives us a bigger gradient between the alveolar PO2 and the blood PO2 driving diffusion into the bloodstream. We once again rapidly equilibrate, right? We still reach saturation, making sure that we're carrying enough oxygen away from the pulmonary alveolar surfaces, even at this higher blood flow rate. This is absolutely essential. Now, what we find is that if the alveolar PO2 were to fall, as it might at high altitude, or for another reason, we might have reduced diffusion due to a pulmonary disease, like increased distance or loss of surface area, what we find is those factors would slow down our diffusion, and we would not equilibrate as quickly, and we would end up with a line that looks a little bit more like this. This means we would not fully saturate our pulmonary blood with oxygen, and we'd be minimizing our delivery of oxygen to tissues in a time of need during exercise. And therefore, people with respiratory diseases or at high altitude often demonstrate significant fatigue.